Hi, in this video I'm going to talk about the differentiation property of the Fourier series. Now, suppose that x of t is a periodic signal with fundamental period capital T0. So x of t will have the Fourier series representation k running from minus infinity to plus infinity ak e to j k omega 0 t, where omega 0 is related to the fundamental period t0 by means of this equality. Omega 0 is 2 pi over t0. Okay, AKs are the Fourier coefficients of x of t, or we can use this notation we have used before. AKs are the Fourier coefficients of x of t. Now, what can we say about the derivative of x of t? Now, the derivative of x of t with respect to t is also periodic. It is easy to see this with also the same fundamental period, with fundamental period capital T0. Therefore, dx by dt, the derivative of x of t, will also have a Fourier series representation. Let us call the coefficients bk. bk e to j k omega 0 t, k running from minus infinity to plus infinity. So what is the relationship between bk and ak? Or first, in terms of our notation we use for Fourier series representations, dx by dt, the derivative of x of t, has the Fourier coefficients bk. So our aim is to find bk in terms of ak. Now, we can obtain the result very easily as follows. Now, x of t has the Fourier series representation. Therefore, we can look at the derivative of the Fourier series representation term by term. Here we omit some technical details related to the interchange of the series operation and the differentiation operation. But suppose that we differentiate, we are able to differentiate the Fourier series representation term by term. So we have ak. Now the derivative of e to jk omega 0 t is jk omega 0 e to jk omega 0 t. Okay, so it is now clear that we can identify this term ak times jk omega 0 with bk. So the relationship between bk and ak is jk omega 0 ak is equal to bk. So we are able to find the Fourier series coefficients of the derivative of a periodic signal, which is also a periodic signal, by means of this relation. Now, in this example, we are going to calculate the Fourier series coefficients of the derivative of the rectangular pulse train. So we start with the rectangular pulse P of t, which is equal to A over the interval from minus t cap over 2 to t cap over 2. It is equal to A. And x of t is the periodic extension of this P of t. So P of t minus m t0. And we can choose t0 to be greater than t cap to avoid overlaps. Remember, for the case t0 equal to t cap, we have the sawtooth signal as a special case. Now, x of t is periodic, remember, with period capital T0, and the Fourier series coefficients are, we have obtained this in another video, a t cap over T0, sinc k t cap divided by T0, or explicitly we can write down the sinc function as sine k pi t cap over T0 divided by k t cap, again k pi t cap divided by T0. Okay, now how can we obtain the derivative of x of t? Now the signal x of t is the periodic extension of P of t. Therefore, the derivative of x of t must be related to the derivative of P of t. So let us look at the signal which is defined as the derivative of P of t. Now this signal is in fact composed of two impulses. Why? Because P of t is equal to 0 outside this interval from minus t cap over 2 to t cap over 2, and within that interval it is equal to the constant value a. So the derivative is 0 everywhere except these 2 points, minus t cap over 2 and t cap over 2. Now at minus t cap over 2, the function jumps from 0 to the value a. So it is a positive jump. Therefore, it's an impulse with a positive strength, which we denote by a. So this is the impulse at minus t cap over 2. Now the other impulse, which is located at t cap over 2, will have a negative strength because it jumps from a positive value to 0. So it will be the impulse with a weight which is equal to minus a. Okay? Now, we can obtain x of t as the periodic extension, we can obtain the derivative of x of t as the periodic signal which is the periodic extension of this signal dp by dt. So it is dp by dt evaluated at t minus m t0. Okay, now this signal will have the Fourier series coefficients bk, which will be related to AKs as j k omega 0 ak. Okay, so how can we calculate bk explicitly? So we have, in fact, a t cap over t0 is the constant term in ak. So we have the product of jk omega 0 and sine k pi t cap over t0 divided by k pi t cap over t0. So in fact, we have a cancellation here. Remember, we have, when we first obtained this expression for AKs, the Fourier coefficients of the periodic pulse train, we have, in order to be able to use the sinc function, we have some apply some modifications in the overall expression. That's why we have obtained these terms, which eventually, in fact, cancel out. As you see, t cap over t0 will cancel out with this term over here. And we write this as a jk omega 0. Also, we have a cancellation of k's. K will cancel out. So we have j omega 0. Then we have sine k pi t cap divided by t0 divided by pi. Okay. Now, we can go on with this expression as follows. Remember, artificially, we have introduced t0 in the expression of this sine function by substituting, instead of omega 0, 2 pi over t0. So we can here do the following. In fact, omega 0 is 2 pi over t0, and we have sine of k pi t cap over t0. Okay, divided by pi. So there will be a cancellation of these pi's as well. So we have a over t0 j times sine, we have also 2j sine k pi. Okay, there is no need to write this because we have nothing in the denominator now. sine k pi t cap over t0 multiplied by 2j, sorry. Okay, let me write it here. Multiplied by 2j. So these are the Fourier coefficients of the derivative of x of t. In fact, just to verify that we have the correct result, we can do the following as an exercise. Let us evaluate bk's directly. So this is how we obtain bk's from a case. That means the Fourier coefficients of the original signal. But bk can be also obtained as 1 over t0, the integral over, now as long as you integrate over a period, you are okay. So from minus t0 over 2 to t0 over 2. And in that interval, we have these two impulses. So those two impulses are A delta of t plus t cap over 2 minus A, the impulse located at t cap over 2, t minus t cap over 2, okay, e to minus jk omega 0 t integrated with respect to t. Okay, so this turns out to be 1 over t0. Now remember that when we multiply a function by an impulse and integrate, we sample the value of that function at that point. So we have, in fact, the term a can be taken outside the integral. So we have e to jk omega 0 t cap over 2. Okay, this is the sampling operation of the impulse at t equal to minus t cap over 2. So we substitute minus t cap over 2. And the second term will be similarly e to jk, but now with a minus sign, omega 0 t cap over 2. Okay. Now we recognize this expression as a over t0. This is related to the sine function. In fact, this is 2j times sine k omega 0 t cap over 2. Now, just to verify that the two results are equal, we have in fact 2ja divided by t0 sine k. Now instead of omega 0 we can write 2 pi over t0, then we have t cap over 2. Okay, so we, as you see, this expression is just sine k pi t cap over t0. So in this way we are able to verify that the direct calculation of the coefficients are in fact we obtain the same result by calculating the coefficients by using the differentiation property. Now, as the second example related to the differentiation property, let us start with the following P of t. So P of t is the function or signal again from minus t cap over 2 to t cap over 2. It is non-zero, and in fact the expression of P of t is as follows. It is equal to at. Here a is a constant. Say we choose it as a positive constant in our particular case. So this is for t in the interval, okay, minus t cap over 2 to t cap over 2 and 0 elsewhere. We have this P of t, and we obtain the periodic signal as the periodic extension of P of t as follows. M running from minus infinity to plus infinity, P of t minus mt0, where we can choose this t0 greater than t cap, again to avoid overlaps. Remember, we have seen this signal before. For the case where t0 is equal to t cap, in fact, we get the sawtooth signal. Well, x of t will have a Fourier series representation, k running from minus infinity to plus infinity, ak e to jk omega 0 t. Here omega 0 is of course equal to 2 pi over t0. So x of t has the Fourier series coefficients ak. Now we have calculated these coefficients explicitly in another video. Remember, in the calculation of the Fourier series coefficients, we have the integral of at over a certain interval, in fact from minus t cap over 2 to t cap over 2, at multiplied by the complex exponential term in the integrand. Okay, so we have used integration by parts to evaluate the Fourier series coefficients. Now we can obtain the Fourier series coefficients ak by considering the derivative of x of t. Now the derivative of x of t will have the Fourier series coefficients bk, and bk will be related to ak as follows. Jk omega 0 multiplied by ak will be equal to bk, and we can, if we can calculate bk, we can obtain ak from this expression. Now let us see whether we can be able to do this. Now the derivative of x of t will of course be related to the derivative of the p of t we have given at the beginning of the example. So first we can start with the expression of the derivative of p of t. Okay, the derivative of p of t will be, in fact, it will be 0 outside this interval, which is from minus t cap over 2 to t cap over 2. However, as you see, again we have jump discontinuities. So at these jump discontinuities, we have the derivative becomes an impulse. Okay, so at minus t cap over 2, we have a jump from 0 to a negative value. Therefore, that negative value is in fact minus a t cap over 2. So we have minus a t cap over 2. This is the strength of our impulse. At the impulse is at t cap over minus t cap over 2. Now similarly, we have an impulse at the other discontinuity located at t cap over 2. So at t cap over 2, again we have a jump from the value a t cap over 2 to 0. So it is again a negative jump. So we have minus e a t cap over 2 delta t minus t cap over 2. Now, in between, the derivative of at, the function at, is equal to a. So that will be, in fact, a rectangular pulse with a magnitude a. So let us show that by p cap of t. Okay, p cap of t is, let me just draw the graph here. This is the point 0, so this is the graph of p cap of t. So it will be equal to a from minus t cap over 2 to t cap over 2, and it will be 0 outside that interval. Now, therefore, we can find the we can define the signal, which is the derivative of x of t, as the periodic extension of dp by dt. Okay? So that's how we define the derivative of x of t. Now, therefore, dx of t by dt will have the Fourier series coefficients. Let us show them by bk. And bk will be equal to, now by inspection, we have these two impulses and we have the rectangular pulse. And we already know how to calculate the Fourier series coefficients of such components. Okay, the periodic repetition of the impulses. Okay, so we have minus a t cap over 2 is the common term. So for the impulse, for the periodic extension of the impulse located at t cap over 2, we have 1 over t0 e to j k omega 0 t cap over 2. Now, for the other second impulse, periodic repetition of the second impulse, the signal obtained by means of that periodic extension will have Fourier series coefficients 1 over t0. Now we have e to minus jk omega 0 t. Then plus we have the Fourier series coefficients of the rectangular pulse train. We already also know that expression as a t cap over t0 sinc k t cap over t0. So we can obtain AK as follows: BK divided by JK omega 0. Okay, here there is an interesting detail. In fact, as you see now in the calculation of the coefficients AK, we have division by JK omega 0. And we may have a problem for the case where K is equal to 0. However, we see that when you evaluate the derivative of a periodic signal, for instance, in this particular example, we have x of t and we have the derivative of x of t. Now, in x of t, the constant term a0, the constant, the Fourier series coefficient a0 will disappear in differentiation because a0 is a constant and its derivative is 0. Therefore, in the representation of the Fourier series representation of dx of t by dt, the derivative of x of t, b0 turns out to be equal to 0. Therefore, we obtain we can obtain AK from BK by taking that into account. Okay, thanks for watching.